Hi everyone, this is Dr. Hopkins, your virtual physical chemistry instructor with the second of our series of videos that we're going to use to replace in-class lectures, which we can no longer do courtesy of a viral pandemic. So what we're going to do is we're going to build on what we've just finished. So we finished vibrational and rotational quantization. And we're going to build on that rotational quantization by quantizing the rotation, well, even in the radial part as well, of electronic motion about a nucleus. So we're going to start to build atomic structures. We're going to start with the basics, though. The simplest system, the hydrogen atom. And so the hydrogen atom is covered in chapter 9. It's all one chapter. That chapter covers only the hydrogen atom because it is so important to our understanding of the rest of multi-electron atoms and in molecules itself. And it's also the last system that we can actually solve analytically. So when we end up with a second order differential equation, we can actually solve this second order differential equation. If we add another electron and say, hey, this is helium, we no longer can solve it, and we either have to approximate our solution or have a numerical solution. And so what this video is going to do is we're going to go through and solve the Hamiltonian. And then future videos will describe how to use the functions and so forth. So solving the Hamiltonian, the Schrodinger equation, we have to set up the Hamiltonian operator. This is fundamentally a two-particle problem. We have a proton and an electron. So you have the kinetic energy of the proton, kinetic energy of the electron, and the potential between the two, right? So the Coulombic interaction between those. Turns out we can make it much simpler because we can ignore the kinetic energy of the proton because essentially all of the mass is in the proton. So if the proton's moving, the particle itself, the center of mass, is moving, which is basically translational motion. And we've already talked about quantized translational motion when we talked about the particle in a box. So our Hamiltonian simplifies to just the kinetic energy of the electron and the potential energy. And so we have that del hat squared. We've seen that operator before. I'm not describing it or not showing it for Cartesian coordinates. It's just the second derivative with respect to x, y, and z, because we're not going to solve this in Cartesian coordinates. We're going to solve it in spherical polars. You'll notice, you'll look at the third term. That third term should be familiar because that's what we used to solve the 3D rigid rotor, where we had a Legendrian operator, 1 over r squared, but now we also have partial derivatives with respect to r that factor in. We have our Legendrian, which gives our angular potential, or our angular part, to the rotation of the electron about the nucleus. And so that's our kinetic energy operator, our potential energy operator. We just have to factor in centrifugal potential, so how fast the electron's moving can affect its energy, and the Coulombic interaction, so how the nucleus is interacting or the proton is interacting with that electron. And you see the two parts. I have them flipped. The centrifugal potential is the beginning. The Coulombic is the second one. There is an r dependence and an r squared dependence. That's the distance between the electron and the proton. You'll also notice I have included the nuclear charge, the Z, maybe somewhat not necessary, but because Z is 1 for hydrogen. But when we go to multi-electron atoms, that's going to factor into our potential. So we have the potential. Now we have our operator. We just have the Schrodinger equation. We have a second order differential equation. If we set that up, now if we had this in class, I probably would show a lot more about how you separate the variables and whatnot. So we can end up separating the radial and the angular parts, and you solve the second order differential equation, and you end up with this wave function here. It's a function of NL and M sub L. We're left with our y, this y term is a function of L and M sub L. That was our solution from the rigid rotor, the spherical harmonics. So you can go and look up what those functions are in the book. And then we get a new radial function, which is a function of n and L. So both of them are functions of 2 of the quantum numbers. And that's a function of the r. And so our n quantum number is allowed to be any positive integer. It can't be 0 though. And then our L quantum number and M sub L quantum numbers are the same as what we derive for our rigid rotor, with the exception that L can only go up to n minus 1, so it can't go all the way to infinity. Then our solution is our eigenvalue, the energy of a hydrogen atom, depends only on L. So L and m sub L, so how fast the electron is spinning and where it's spinning and which direction it's spinning or rotating around, I should say, not rotating, not spinning, rotating around the nucleus. None of that matters in terms of the energy for a hydrogen atom, at least. So we have all of our fundamental constants, the mass, but the only quantum number in there is 1 over n squared, which simplifies if you just add all of those fundamental constants together. The last part of that equation, 2.18 times 10 to the minus 18, you might remember, or you might not, may never have thought about it, is the Rydberg constant. And so that is the solution that Bohr came up with the Bohr model for hydrogen atom in terms of joules. I think your book publishes this energy, or talks about this energy in terms of EVs, which if I'm not mistaken is negative 13.6 EVs in terms of EVs. But this is what it is in joules. And so next time what we're going to do is we're going to take these solutions and we'll talk about what the quantum numbers mean. We'll talk about what the angular momentum and the angular momentum of those solutions, what the new radial functions give us, so how we can use these wave functions to understand the hydrogen atom structure, which then we will build on to do multi-electron atoms.